welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
I'm Connie, and I do want to be the universe's friend, and I love that you can tell me about it.
Connie, you are the universe's friend.
Indeed.
I know that because I'm friends with the both of you. I've seen your relationship flourish.
It's been growing, you know?
It's beautiful to see. Hi, everyone. I am Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe. I'm recovering from a cold, so C's are really hard right now. But we're gonna get through it on this episode
this is more about of a Q episode.
Yep, that's a C sound.
Oh,
it's okay. I'm so excited to be breaking down a really storied topic. Like you can go see movies about the quantum realm. You can hardly read or watch any sort of sci-fi without hearing about quantum entanglement or quantum phasing or whatever.
Yeah.
So today we're going to hopefully make that a little bit less mysterious. It's going to make a little bit more sense by the end of the episode. But I want us to take a deep breath before we get into it. And out. Yeah, because we're going to dive into some pretty heady topics, and I'm not going to tell you a lot of math, but I'm going to tell you some math.
Okay.
So there will be some exponents, there will be some Greek letters.
Oh dear.
That's okay. We're going to face each one as we come to it.
Good. Okay.
What's your greatest impression of quantum stuff?
Probably the MCU's Ant-Man.
Okay.
But even those movies are not really on my top tier lists. So I've seen them maybe once. And the other is Quantum of Solace as a title. That's about it, really.
Is that a Superman thing?
It is James Bond.
It's James Bond. Well, I want to talk about where quantum started. I know a few episodes ago, we did some of the history of electromagnetism and leading into some particle physics stuff. But I want to tell a little story that will reveal the origin of the word quantum itself.
Okay.
In a physics context. The first person to start using this in a physics or science context was Max Planck in the year 1900 when he imagined energy not existing or being emitted in a continuous process. Something not a star emitting energy just all the time, but in discrete quantized packages. And a quantum was the minimum amount of energy or the minimum energy threshold to be released at a time. This idea of energy being released in quantized discrete packets was part of Max Planck's solution to something called the ultraviolet catastrophe, which I think would make an amazing mystery novel title.
Absolutely.
So to set the scene for the ultraviolet catastrophe, we have to go back to black bodies, which we've talked about a little bit before. Do you remember this?
I don't.
Okay.
I went somewhere very different.
This has happened a few other times. I've brought up black bodies as well. So black bodies are ideal model objects in physics. And, obviously.
Oh, well, I'm agreeing with it even more already.
They are ideal model hypothetical objects that absorb all electromagnetic radiation and then don't reflect any of it. It's all absorbed, and then it's re-emitted as thermal radiation. And we most closely associate thermal radiation with infrared, but if you are at higher temperatures, you can be emitting at different parts of the electromagnetic spectrum. So you can be shining in all of the wavelengths of light, but you can create a curve, a line, a black body curve that measures how much energy you get at the different wavelengths of light. And starting in the late 1800s, when scientists are simultaneously really interested in the burgeoning field of thermodynamics, so the study of temperature and energy, and also getting really detailed information about stars kind of for the first time, because we have spectrometers that can break up the light from stars into different wavelengths. And so that kind of combines to get people interested in these black body curves, because stars are an approximation for a black body object. They're not perfect. They don't perfectly absorb all electromagnetic radiation, but they do a pretty good job. But there are other objects that could theoretically be a black body. You could have a black hole, which absorbs everything. It doesn't reflect anything away. But then you have the event horizon around it, which is like thermally emitting because of all the energy in the system. Even if you have a box and you paint the walls on the inside of the box black, and then you poke a little hole in it so that it can let some light through. That light can go in through the hole, but it gets bounced around. Well, actually, because the walls are black, it kind of just gets absorbed by the walls. If any of it does reflect, it reflects to another wall and gets mostly absorbed. So the light can come in, but it's really not getting out. So a black body is like a Hotel California, but for light.
I want to say they did something with this in Ryan Gosling's latest movie, Project Hail Mary. I can't remember exactly, but they're studying these like things from the sun that's going to destroy the sun, and they do like construct like a big black box in like a random place. Yeah.
Nice. Yes. They might have constructed their own black body box.
Probably.
And so those physicists at the time who are really interested in thermodynamics and also stars, they start trying to mathematically figure out what the shape of the black body radiation curve should be. So how much energy should a perfect black body object be emitting at different wavelengths? And they can produce black body objects of different temperatures in labs and then observationally figure out how much energy is being emitted at different wavelengths. But different scientists have to use theory and some math to figure out what the curve will look like outside of the temperature ranges that we can produce here on Earth. So like, the temperatures of stars.
Right.
We can't really produce that here easily. In 1897, like right before Max Planck coins the term quantum in science, a German scientist, Wilhelm Wien, although he goes by Willy Wien on the paper.
Wouldn't you?
It's so funny because it's in German.
It's so modern.
So it's like 1897 on the division of energy in the emission spectrum of a black body, and then it just goes von Willy Wien.
Triple V out here, doing his thing. But it's so modern. Like, I just want to go by Willy Wayne.
This is the Tiffany effect in real time.
Yes, it is.
Yes, it's actually it's actually a really old thing.
Yeah.
But yeah, so he publishes this paper where he has his own mathematical formula for what the shape of this black body radiation curve should be. And it's a function, it's a mathematical function for the radiance or the brightness or like the energy output of an object as a function of wavelength and temperature. And when Wien makes his approximation, the radiance is proportional to 1 over the wavelength to the 5th power. And then there's this other like exponential term with like the letter E that has the temperature term in the exponent. And so really it's a 1 over wavelength to the 5th. That's what you have to remember.
Okay.
This, when you solve for where the maximum peak, where the peak of the radiance should be at what wavelength, this gives us Wien's displacement law, which says that the wavelength where the energy peaks is going to be inversely proportional to the temperature. So if you have a higher temperature object, it will have radiation energy that peaks at a lower wavelength.
Oh.
So hotter objects,
sure,
smaller wavelengths, right?
That
yes,
does
because
make
hotter
sense.
objects, more energy.
Yeah.
Yes. His formula does a good job at matching the experiments for short wavelengths,
Right.
but not really for the longer wavelengths. So then in 1900, a few years later, Lord Rayleigh, who later works with Sir James Jeans to make the Rayleigh-Jeans law, Lord Rayleigh develops his own formula, and his formula for the radiance, for the radiation energy, is proportional to 1 over wavelength to the 4th instead of to the 5th power. And there's no exponential term that houses the temperature component. And this formula matches the observations at long wavelengths, but not at short. So if you could magically combine the Rayleigh approximation and the Wien's approximation for these blackbody curves, then you would actually be able to match the observations in the lab.
Okay. Science.
Science.
Math.
Yes.
The power of math.
So Rayleigh and Jeans, their approximation stops working at the short wavelengths, which is where the ultraviolet part of the spectrum is. And they, if you follow their formula, you would actually have an infinite amount of energy by the time you get to the ultraviolet wavelengths. And this is deemed either the Rayleigh-Jeans catastrophe or the ultraviolet catastrophe.
Because that one is more specific. It's like if you're just talking about 2 names, I don't know what it is. That one, ultraviolet catastrophe, that's serious. That I already know. It's like, whoa. I'm interested. I'm curious. I don't know who Rayleigh and Jeans are. Well, now I do.
We do need better names to go along with them. And so we needed a solution to the ultraviolet catastrophe. And Max Planck comes along and figures out a way to combine the Wien's approximation and the Rayleigh-Jeans approximation. Max Planck is coming from the context of, electromagnetism and thinking about the wave-particle question. And he proposed a formula that relies on the idea that black bodies don't continuously emit their radiation.
Oh,
that
right.
they actually can emit their radiation in like little bundles. Like in when I say discrete, does that mean something to you? Like as opposed to continuous? So you have continuous, which is like
in that context, it seems like individual, like discrete. Yeah.
Yes. It's individual packets. It's like not the whole bag of Twizzlers, but a whole bag of individually wrapped Twizzlers.
Okay. Thank you for choosing
that
Twizzlers.
Was my example.
But I love Twizzlers, so
Fantastic.
It must be something in the bestie spectrum because I don't even know if I've told you that.
So it's not that the black body radiation is emitted as just like a full continuous swarm. You have to buy an individual packet of Twizzler from the black body radiation curve. I don't think I'm doing this metaphor justice.
It's helping me, so.
Great. Basically, it means that you have to meet a minimum energy threshold to put yourself into a packet before you can move away from the black body object, before you can be emitted away. So there are these minimal increments that Max Planck called quanta. And quantum is a singular. And so he introduces this term to science, and it turns out that there are a lot of places where the idea of like discrete individual packets is useful and relevant. And so that is the realm that we assign quantum to. Anytime you have to deal with photons, which have like specific amounts of energy, or electrons in their energy levels around an atom that have like specific amounts of energy in each level. And they can only move up to the next level if they get a specific amount of energy. It's not like you could exist between the energy levels if you get half the amount of energy you need. No, it's like one or the other. Yes, it's discrete. That one or the other thing is going to sound confusing later because the whole thing about quantum is that it's actually not one or the other. It's both and everything all the time.
Everything all at once.
Yes. But more on that in a second. So this is where we get the term. Also, around the same time, like the early 1900s, scientists are discovering the electron. They're developing and perfecting light spectrometers and developing different types of spectrometers to manipulate light in different ways. In 1913 is when Niels Bohr proposes the atomic model where you have electrons in energy shells. So it's not a perfect model. We now know that electrons are more like clouds of possibilities around the nucleus of an atom, but the Bohr model did give us the idea that there are like discrete quantized energy levels within the electron paths around a nucleus.
So you mean like the model that we maybe saw in textbooks as kids, for those of us who didn't follow the trail, it used to, at this time, 1913, be like each electron were their own little thing, and now we understand it as more of a cloud of things.
Yes.
Around it.
Niels Bohr's model was kind of like a solar system where the atom was the whole solar system, the sun was the nucleus, which housed the protons and the neutrons, and then the planets were all of the electrons, but they would follow on the same orbital paths, and you could predict where the electron would be. We now know that it's more chaotic than that.
Yeah, but no, that's an interesting thing about that diagram, because it does kind of make it a 2D plane and not like a 3-dimensional. Yeah, it makes you think of it so differently. Huh.
Mm-hmm. I mean, I think even some of the Bohr drawings had them in 3D, not just in a flat plane.
Okay.
But it's even the 3-dimensional model of set orbits is too neat compared to what is actually happening.
Okay.
So that's the Bohr model, which came out in 1913. In the 1920s, people are really excited about quantum explanations for classical things in physics and science. And so we get the electron cloud model, which is the quantum mechanics model of the atom.
Okay.
So that is where quantum stuff starts. It's the late 1800s, early 1900s. It is based on the idea that at the most fundamental scales, energy is paid in like specific intervals. When energy, like a photon, gets injected into an atom, it's a specific amount of energy, and then that atom can move its electrons with like that amount of energy that it got paid.
Okay.
From that idea, when you start looking at the natural world, you start to notice some very weird things. I'm going to point out 4 very weird things that are kind of like the 4 pillars of quantum mechanics. These ideas set the foundation for a quantum philosophy. Okay. I think that might be the best way to think about it. You don't have to think about it in equations, but these concepts, if you can grasp them, will help you develop a quantum philosophy that scientists have taken and run with. And so, like quantum computing, any sort of like quantum research, it is based on this philosophy.
Okay.
That uses equations, but we don't have to talk a lot about the equations.
Okay? Great.
The first pillar of the quantum philosophy is wave-particle duality, which we talked about a little bit in our microwave episode. In that episode, we talked about how wave-particle duality is not just for light. It's not just that light is a particle and a wave, but that every particle that has charge or moves is both a particle and a wave, that everything has this wave-particle duality.
Okay.
And so that's kind of just like a thing that you have to accept. Move away from the idea that particles are like little balls moving through the universe, that they are rigid and that they always exist, and that this like individual particle ball can move from place to place.
Yeah.
Get rid of that.
Yeah.
That's not true. And when you do math or when you do observations on really small or really large scales with that assumption, things break down.
Yes, they do. That's what breaks my brain often.
So instead, based on our observations and our math, it is more accurate to think of these particles as temporary spikes in fields of energy.
Okay.
Think of each of those fields kind of like, you could think of it as a field of grass, or you could think of it as an ocean. But a spike is either going to be, like a little drop that comes out of the ocean, or a blade of grass in the field. It is there for a little bit. It can move. It can interact with things around it. It will eventually return.
Okay.
Mm-hmm. Great. When you start thinking about particles not as balls, but as spikes of energy, you can more accurately describe them in terms of waves moving through that field.
Yeah, I liked ocean as a...
Okay, fantastic.
Yeah, mm-hmm.
Okay, so like a tiny wave moving through the ocean, and each particle is its own little wave that can appear and disappear, and it can move, it can interact with other things. The tricky part here in this metaphor is going to be that there are actually multiple overlapping fields at once, but we'll get to that later.
Yeah, okay.
The most persuasive evidence for this, that every particle is actually a wave, is the double slit experiment. I think the first time this was done was in 1801, but it's been done a bunch of times since then. It's been done with light and electrons and different types of particles. If you have something that can send out particles, let's say it's a laser beam, it can send out photons, and you have a wall where the photons eventually end up, but between the source of light and the wall, you have another wall that has two slits in it.
So they're parallel to each other, but one has the two slits in it.
Yes, exactly. You might expect, if you've never heard about the double slit experiment, that the light will just pass through and you would see two light strips behind the gaps in the wall closest to you on the farthest wall.
Yeah. So I imagine like the light going out, I can see it against the wall in front of me. The other two lights are going through the slit, and I imagine they must be hitting the other wall behind it.
Yes. But that is the scenario where the photons just follow the straight path, like from the gap to the wall behind it, and they don't go anywhere else. But that's not what we observe.
No?
So that's clearly not the case. What we see is an interference pattern. We can see like ripples of light going out from the center of the wall and getting dimmer as you go away. So it's like there is a bright strip of light in the middle, and then two slightly less bright strips of light on either side of that, so on and so forth, with darkness in between. There's like ripples in a pond. Those are actually interference patterns, constructive and destructive interference patterns that you get when you add up the waves of light that are hitting the walls over time. This same thing happens if you send electrons at the wall. So it's not just about light operating in a weird way. You can also see a buildup of electrons in this interference pattern. Even if you send one electron at a time, so presumably it's just one electron ball, it shouldn't know about this wave pattern. It has nothing else to be interfered by. So you should get all of the electrons in the same place. No. Even if you send one electron at a time over and over and over again, you still end up with this interference pattern, as if the individual electrons are also interfering with themselves.
So the double slit wall is the representation of interference?
I mean, it shows the interference patterns that happen. If you were doing this same experiment, but with water, with waves of water passing through two gaps in a wall, you would see the ripples of the water, the waves of the water, as they hit on the other side.
Oh, okay.
Like you would actually be able to see the interference patterns in the waves as they pass through the slits in the wall closest to you.
Okay. Yeah.
So what we would expect to happen with water, but not with particles, still happens with particles, which shows us that the particles are behaving as a wave.
Okay.
Even individual particles sent one at a time still behave like their own wave. Another very confusing thing that comes up with the double slit experiment is this question of observation. Particles seem to behave a particular way when you are observing them, and another way when you're not. And so it's almost as if they are aware, are conscious of being perceived. That is not the case. That is a function of the uncertainty principle, which we're going to get to in a second. But people do talk about that with the double slit experiment a lot. By observing this experiment, we are interacting with the particles themselves and forcing them into a specific state. So they are going to look like that when we observe them.
On Doctor Who, there is a villain that is similar to this, where the Weeping Angel, that if you look at them, they are frozen, but if you look away, they move and they attack you and kill you and take you through time and absorb your energy or whatever. So might be where some of the inspiration came from.
But it's not that the particles stop moving when we look at them, but we can more precisely measure different quantities. I'll get to the Heisenberg uncertainty principle, but first I need to talk about Schrödinger and wave formulas.
The Schrödinger?
The Erwin Schrödinger of cat fame.
Of cat fame.
He's the most famous to have mathematically described the motion of individual wave particles. So if in classical mechanics, you could use Newton's laws to describe the motion of like a ball type particle. But if the particles are waves, they don't move in the same way. Mm-hmm. And you need extra things to define their motion. Mm-hmm. And so in 1925, Erwin Schrödinger created a differential function that shows how the wave changes over time. And his equation is often shown with the Greek letter psi, the one that looks like Neptune's trident, kind of, but cursive.
Mm-hmm. I love that.
And his equation dictated that the total energy of the system had to stay the same. So the total energy is the kinetic plus the potential energy. And he said that, to describe the wave motion, you have to say, like, how is the wave actually moving? How is the wave getting energy compared to its surroundings? It's like its potential energy just based on what is around it in the space. If you add those up, they have to be conserved. A consequence of this wave behavior of particles, or another way of understanding the wave behavior of particles, is that they don't just exist in one place. Remember, they're not a ball, they're a wave, and waves go on forever. So a particle actually kind of exists everywhere. There is a whole breadth of possibilities for every particle. They can be at the top of their wave or the bottom. They can be at the end or the beginning of the wave. I don't know. But because there's this cloud of possibilities, that means that you have to kind of imagine that the particle exists in all of those possibilities at once. And this is where Schrödinger's famous cat thought experiment comes in. Mm-hmm. This is like the fundamental quantum thought experiment. If you have a cat in a box and there's a radioactive isotope that has, a quantum possibility of decaying into a dangerous isotope and killing the cat, before you open the box and observe the system, it exists in all states of possibility. And it's only when you measure or observe the system that you force it into a particular state. And so that's where the weirdness with observation and quantum stuff comes in.
Mm-hmm. Okay.
Mm-hmm. And so quantum math actually involves a lot of statistics, a lot of probabilities, because you can't say with certainty this particle is in this position, moving at this speed in this direction. Instead, you can say, based on the energy in the system, this particle is most likely to be in this state at this place.
Mm-hmm. Okay.
And that idea that the particles can exist in multiple states at once is called superposition. So it's both and all at once.
Mm-hmm.
The reason you cannot precisely know all of the information about a particle, its position and motion, is because of Heisenberg's uncertainty principle. This principle was postulated in 1927 by Werner Heisenberg, and it says that the more precisely you know a particle's position, the less precisely you know its momentum. Momentum is mass times velocity. So the more you know about its position, the less you know about its motion, and vice versa. The more you know about its motion, the less you know about its position. And this is represented mathematically by saying that the uncertainty in position times the uncertainty in momentum has to be greater than or equal to some constant value. It's a value that is related to Planck's constant. And you don't need to know what Planck's constant is, but you do know that Planck came up with the word quantum for physics. So his constant is pretty important.
Yeah.
Yes. And so if your uncertainty in position goes down, you have to get more uncertainty in momentum in order for this multiplication to be larger than that constant value. So that's the math of it. But conceptually, I watched this video by Dr. Katie Mack, who's a theoretical cosmologist at the Perimeter Institute in Canada. And I really liked how she put it. The video is linked for patrons in our research notes. But because everything is a wave and waves move and they go on forever, they're not in a fixed point. If you want to understand the position of the spike in that wave, you have to ignore the other information, or you have to collapse the information to be in a particular location. So you lose the rest of the wave information. But if you want all the wave information that tells you where the wave is actually going, you cannot focus on a particular point in space because the wave is moving through every point. So you have to sacrifice some knowledge. Odin, the Norse all-father god, would understand.
Indeed.
He sacrificed his left eye for knowledge. Yes, he did. and so that is kind of embarrassing that there is a limit to our precision, because so much of Western science is based on getting more precise values for everything. But apparently there is a real limit to how precise we can get. And I love that. Hi friends, it's me. Connie is playing with my quantum microscope right now. You can't actually look at it for too long because forcing all of the particles into an observed rigid state creates an unpleasant buzzing sensation for the viewer. But we have a couple of minutes, so I'm going to share some messages with you. First, you already know our merch pre-orders are open. The Oracle deck won't be ready until August because we want to make sure that they are the best Oracle deck cards for you possible. But everything else is available and amazing. You can order at certifiedcrucial.com or check out the link in the episode description. My next message is, of course, a thank you to all the patrons who support the show. We're an independent podcast, so we rely on support from listeners like you. You know, we're just like PBS in that way. A special shout out to our sun-like stars, Scott Reynolds, Tom T., Seven Petrichor, Ashley Shambo, Bruce Sedloff, and Kelly Bennell. Thank you so much. You're golden and you're perfect. If you want to join these stars and support this indie podcast on Patreon, you'd get to hear your name on the show, make it onto the patron star chart, and get research notes for most episodes for $5 a month. All of that at patreon.com/palebluepod. But of course, that link is in the episode description, as is our PayPal link. In case a monthly subscription isn't for you, you can make a one-time donation and become a supernova in the Pale Blue Pod sky at the link in the episode description. And of course, if you can't support us financially at all right now, we understand. Things are hard. Money is weird. We don't want you to spend your hard-earned money on us because we are just grateful that you listen to us at all. If you still want to help the pod, you can rate and review us on whatever podcast platform you use, and you can share it with someone who you think would actually like the show. But no matter what, thank you for listening. Connie and I are honored to be a part of your week. My next message is a podcast recommendation. It's another show in the Multitude Collective called Dreaming Against the Machine. This is a podcast about envisioning a realistic and hopeful future. Each week, the show's host, a journalist and astrophysicist, and a friend of mine, Dr. Adam Becker, will have an earnest and entertaining conversation with a guest about possible futures, seen through the lenses of history, science, and culture. In a world where tech oligarchs and their power fantasies are driving visions of the future, Dreaming Against the Machine aims to take back the terms of the public conversation about what our world can and should be. Adam just did an episode with physicist and author Dr. Katie Mack about the end of the universe, and she did literally write the book on that, so check it out, or any of their other episodes. New eps drop every Tuesday. Check them out wherever you get your podcasts. Oh no, Connie has the buzzies, so I'm going to go give her a big hug and squeeze to stop that, and then we'll get back to this conversation about quantum mechanics. The last weird pillar of the quantum philosophy, so far we have wave-particle duality, superposition, and the uncertainty principle. The last pillar is entanglement. The idea that on a quantum level, individual particles can become so linked that if you move them apart, changing one will instantaneously create like an equal and opposite change in the other particle.
Oh.
So these linked particles are said to be entangled. This is what Einstein called spooky action at a distance.
Ooh.
But it's not actually very spooky. He called it spooky because if you have these instantaneous effects on the linked particles, that implies that information is traveling between them faster than the speed of light, because how can particle A know instantaneously what particle B did if information isn't exchanged? And all I got from what I read up on quantum was that no, it's just not moving faster than the speed of light. It's just that the two are just linked.
It just is, because you said we have to forget all the other stuff that we already know.
It just is.
Yeah, like we're all linked. Okay.
There are specific ways that you can quantum entangle particles, and they could form quantum entangled. There are ways to produce multiple particles at once so that they have the correct properties. One way that we've actually talked about before is the stimulated emission of photons. Remember when we were talking about masers in the microwave episode? And you get the atom so excited that when the electron can't take it anymore, it spontaneously releases 2 photons instead of 1 to drop down an energy level.
Yeah. And I'll remember it forever now.
The stimulated particles.
And the entanglements, yeah.
And when you generate those 2 photons at once, they are coming from the same quantum process, so they are identical in their identities. And if you get them to be like emitted from the particle at exact opposite angles, then they will have like perfectly antipolar quantum spin, which is like the direction of the spin of the electrons in the atoms. And it's not like the physical spin. It's not like the physical rotation of the atoms. It's just like a different type of value or quality of the electron, like its charge or mass is spin.
Okay.
So they will have completely opposite spins and therefore be entangled because they are the same but opposite. Another way that you can generate these entangled photons is by using something called parametric down conversion, where you split a high energy photon from like a laser beam into 2 lower energy photons by shining that laser at a special type of crystal. Right now, the most effective, or like one of the leading types of crystals for this, is barium borate. So you shine a laser at barium borate, it interacts in such a way that splits the energy from the laser beam into 2 photons of half that energy. If you get entangled photons absorbed by different atoms, you can make those atoms entangled too, which is really interesting. It's like one entangled apple really does entangle the whole bunch. And then, but it seems like I don't want to say the best, but the coolest, in my opinion, the coolest way to get an entangled pair of atoms is to excite atoms into what's called a Rydberg state. Ooh. This is a special state where the outer electrons are so excited, they have so much energy that they are physically farther away from the nucleus than is like any type of normal. And so they're so far away that they can actually influence other particles nearby. I think they produced this once with a couple of rubidium atoms held 4 microns apart. So like that's like a measurable thing. Like we could 4 microns, we can actually excite atoms to the point where they influence each other over that distance. So if you get one of the atoms into a Rydberg state, it can influence a nearby atom into an opposite state, like charge-wise almost, and then lock each other into place where they're holding each other stable, but they're both locked into this kind of superposition Rydberg state where the electrons have a much larger cloud of possibilities. And so it's like extra quantum, and they're entangled, and now you can
extra quantum.
And now you can induce changes on one, like influence its spin and its rotation by spinning and rotating the other. So that's quantum entanglement. And that is useful in some of the technology that depends on quantum stuff. But I want to talk about quantum field theory.
Okay.
Which is like the description, the longer description of all of these particles being just spikes in an energy field. I want to go back to that analogy again.
Okay.
So quantum field theory is how you can combine quantum mechanics and special relativity, because in degular quantum mechanics, the particles can't move at relativistic speeds. They can't move at the speed of light. So it's like, how can you account for photons? How can you account for things out in the extreme environments of the universe? So quantum field theory asks, how do whole fields of wave particles interact with each other instead of just like individual particles behaving on their own? A field in science or in math is a mathematical description of a space or an entity. You can think of it as a multidimensional array of numbers or values, or if you want to go along with the metaphor, it's like a field, and every point on that field has a value for like how much dirt is there.
Sure.
What's the soil composition? It like has a bunch of different values everywhere.
Okay.
This term, field, was initially used in this context in 1845 by electromagnetism pioneer Michael Faraday.
I've heard that name.
Yes, we have talked about him, and he's big enough that you've probably heard of like Faraday cages.
Yeah. If there were fans of Lost, it was mentioned a lot there too.
So he coined the term 1845, and then over 100 years later, in the 1960s and 70s, when they were really figuring out the standard model of particle physics, that term field got applied to quantum field theory. So in the standard model of particle physics, there are 12 different matter particles. So there are 6 different types of quarks. There are 3 different types of leptons, which are the electron, the muon, and the tau. And then there are 3 different types of neutrinos. All of the matter that we see is made up of stuff like that. And then there are 4 force-carrying particles. So there's photons. They carry the electromagnetic force. There's gluons, which carry the strong nuclear force. And the weak nuclear force is special because it has 2 different force-carrying particles, the W boson and the Z boson.
Okay.
There is a 4th fundamental force, gravity, but we have not yet discovered a force-carrying particle for gravity. So it is not part of the standard model of particle physics yet. And then there is another type of particle called the Higgs boson that is responsible for giving the other types of particles, fundamental particles, their mass.
Okay.
In quantum field theory, all of these 17 different types of particles are associated with their own particle field. Imagine that field of grass. I know you said ocean, but like imagine this field of grass.
Okay, we can go back to grass. Mm-hmm.
Yeah, there's also, the air field above it, and there's the water table below, and there are all of these different overlapping fields that each have their own values and can each produce their same spikes, and they can interact with each other. But some of them will interact more strongly with others. Like the water field is very strongly going to interact with the dirt field, but not really strongly going to interact with the air field,
right?
For example.
Okay, yeah.
And for each of these fields, they have like a threshold amount of energy that has to be surpassed in order to create a stable spike in the field. And that stable spike is going to be that type of particle. I can't remember what the exact values are, but it doesn't really matter. Let's say like for an electron, you need to produce like 1 electron volt. You need to produce 1 volt of energy to create an electron particle that can actually interact with other things. And if you don't generate enough energy, then you're not going to get that particle there.
Yeah.
But you can spontaneously produce these particles anywhere along the field. So there's always turbulence in the field. It's always a little bit staticky. And most of them will be produced and then annihilated. They'll be created and then destroyed immediately. And so there's always this kind of up and down. There's always these little ripples in all of the fields. The fields interact with each other by coupling or exchanging energy between each other. So the Higgs boson interacts with all of the other field, not the photon, because the photon is massless, but the Higgs boson will interact with the other types of fields to give them their mass. And the electron it doesn't have a lot of mass, so it's not strongly coupled with the Higgs boson field.
Okay.
Right?
Yeah.
But a top quark is juicy, it's chunky, and it's interacting really heavily with the Higgs boson field.
Right.
But some of the fields don't interact at all. Neutrinos are electrically neutral, so they do not interact with photons, with the photon field, because that is the electromagnetic force field. Gluons, they only interact with quark fields. So they will not interact with electrons, for example. Whatever dark matter is made of, we don't know yet. Like, that's a different type of particle that we're still trying to look for. Whatever it's made of, it does not interact with photons or with gluons. And it may or may not interact with the W and Z bosons, but we're really not sure. It has mass, so it interacts with the Higgs field. But yeah, there is this, like, in my book, The Milky Way, I described it as a computer operating system, and that there are different programs for each of the fields. And some of the programs need to talk to each other, and some of them don't.
Sure, yeah.
But in the universe, there are these 17 different programs, field programs, quantum field programs that are operating all the time in the background without us necessarily knowing.
Yeah. Yeah. Happens on your phone too. There all the background processing and background location and stuff. Those things are happening in the background.
Yes. And that is quantum field theory.
Okay.
And with that knowledge of quantum field theory, and quantum mechanics, we can now do practical things. Any type of technology that depends on exciting atoms with specific amounts of energy to release particular photons, that relies on quantum philosophies. So fluorescent light bulbs. MRI machines. The magnets will align the quantum spin of water molecules in your body so that specially tuned radio waves can map the density of water molecules throughout different parts of your body.
Yeah, that's a lot of programs running at the same time.
Atomic clocks rely on quantum stuff. Lasers, transistors, like so many different types of technology.
A lot of the things that still feel a little bit sci-fi to me. Like, we've had them for a really long time, but it's still like, wow, you go inside a magnet and it can see things in your body. Like, that's still like I get the regular light bulbs, fine. Fluorescence, if they shatter near you, you have to like clean it up specially. and stuff. Like, that's a little still sci-fi, for me.
I didn't know you had to clean them up specially.
Yeah. There's like the material in it is not necessarily, safe for people. So I once broke, like, I think it fell. And when I was looking it up, it was like, yeah, don't touch it or really try to breathe it in. Thanks.
Oh.
Yeah.
Awesome.
Great.
Glad you're still with us, bestie.
Oh, yeah. It wasn't going to be a lot, but it was like, be careful.
Let's see. Another thing we didn't really talk about was quantum tunneling, which is important for semiconductors. Here on Earth, they act as both conductors and insulators of electricity. But out in space, very important for nuclear fusion in the cores of stars. And radioactive decay everywhere in the universe relies on quantum tunneling, where particles can just spontaneously cross barriers that they should not have enough energy to cross. So that's physically crossing spaces, that's passing through obstacles, because remember, they actually exist in a whole cloud of possibilities. And there is a tiny little statistically kind of insignificant tail of that possibility where it has already passed through the thing.
Oh.
And so sometimes, like 1 out of a billion times, it will pass through the thing.
Oh, yeah.
Yes. Yeah, that's quantum tunneling. So that's how we make semiconductors. We just are banking on electrons and other particles being able to quantum tunnel through objects. And we have quantum computing now, which I always thought that this was like a totally different type of computer. Like it needed to be made of completely different types of stuff.
Yeah, that's definitely what I think.
It just applies quantum philosophies to computer systems. That's why I said it's a philosophy system. Like you don't actually need these waveform equations and whatever.
Okay.
You just need to understand duality and uncertainty and superposition, because the way that quantum computing works is instead of using binary code, instead of using bits like zeros and ones, they use quantum bits or qubits. And these qubits can be 0 and 1 and any superposition possibility in between. So it's like they have limitless possibilities, and that lets them process more info. Qubits can also be entangled, so that if you change one, it changes the other.
Okay.
And in order to use these qubits, they do have to use slightly different types of like processors, because the bits, zeros and ones, they're coded with electric pulses. One is on and 0 is off.
Right.
Qubit requires a special superconductor or like a special manipulation of fundamental particles, so that you can like have them in those superposition states. But apparently we're using those in light bulbs. So like, so they do require special processors.
The superconductor thing sounds more like it needs more energy because everything can be turned on or off, versus like sometimes the zeros will always be off, or like in like a regular computing sense, the zeros will always be off. So like that's a certain amount of energy used.
Yeah.
And so they need more energy available.
That sounds right.
Okay. Look at me understanding something.
That sounds right to me. Regular computing is kind of a mystery to me, so quantum computing is an extra gamble. But,
definitely. Me too.
This is now almost everything I understand about quantum stuff. I have bequeathed unto you.
Okay.
How do you feel?
My brain is definitely wrinkled, which, you know what, in this day and age, I'm actually thankful for. But also, that's tiring. That can be tiring. But I think I am at least ready to think of quantum as the possibilities of duality.
Yeah.
Okay. And that brings me back to James Bond, because now quantum of solace could potentially mean the duality of solace. I don't know if it makes sense, but I will look into it later and find out.
It is at least you getting more familiar and comfortable with the material.
Exactly.
And that's the first step here. Awesome. If we think of anything else that remains unclear, I'm happy to do more episodes on this in the future.
Yes, please share your questions, because I'm still processing the first wave of information. So I need some time to process. So if you guys who are listening, if you have questions, please send them or comment them.
Awesome. Yes, please do. We are going to play a fun little quantum game in a second, but first I want to remind everyone that our merch pre-orders are open.
Woo!
So if you go to the link in the description, we will be taking merch orders for the rest of the week, and then we will start making the merch. So let us know how much we need to make by putting in those pre-orders.
Yes,
Thank you in
please.
advance.
Yes, please. So many great items. Moiya, tell us about that you're most excited for.
My top are the silk scarf. I'm really excited for that.
Me too.
Decorated like the aurora in the Pale Blue Pod cover photo. And then I'm really excited for the knitted blanket.
Yeah.
It's going to be like full cotton blanket. Like, I'm so excited for these natural fibers in my life. And I'm really looking forward to the Muses mug, because I want to sip some tea out of my Muses mug when I'm having writer's block.
Oh, yeah. That mug is going to go great for when people get your book out in August. It's happening, guys.
It's happening. Part of the reason my voice is still struggling so much from the cold that I'm mostly recovered from now is because I read the audiobook.
Indeed.
I recorded the audiobook of
this.
Mothers of Invention last week. So my voice box is still traumatized. But so they'll be a good pair.
Indeed.
Bestie, what
Yes.
are you most excited for in our merch items?
Yeah, those are the things I'm excited for.
Awesome. I can't wait to see these orders going out to the listeners. So get your pre-orders in now. Thank you.
Yeah.
Okay. Our fun little quantum-inspired game is a Fight Club kind of Quantum Mania. I have my team of fighters.
Okay.
All different quantum fields. And I've asked Connie to come up with celebrity/fictional character fighters on her own.
Yeah.
And we're going to see who would win in a fight. We'll do a little verbal squabble. So, Connie, would you rather pick your fighter first or have me pick my fighter first?
Pick your fighter first.
Okay, excellent. I am going to throw out the Higgs boson field. I'm starting strong.
Okay. Yeah, real strong. So
Yeah.
in terms of strength from my pick of fighters, I'm going to put up Jalen Brunson.
Respect.
Yeah.
Respect.
Yeah. I was looking for some inspiration from my feeds, and that one came up a lot. So I'm gonna go with Jalen Brunson, who I don't know.
Our dad,
I mean-
Jalen Brunson. That's actually a great move. Because had you picked, like a big fighter and tried to use size against me, the
No.
Higgs boson field would have just manipulated masses so that you didn't have a size advantage.
Absolutely.
But I don't think the Higgs boson field is going to have much defense for Brunson's speed and accuracy with teamwork.
Yeah, exactly.
Does Brunson
Yeah.
have any special moves you think he would pull out in this fight?
A wave. If there would be a Knicks wave, because they act as one. He has been playing with some of them people since college days. So, they can form a quantum entanglement wave and just go at the Higgs boson. That's what I think.
Great job. Great job. Oh, well, I really wish that I had picked my next. Had you picked Jalen Brunson first, I know I would have gone with my next fighter, but instead, I think Jalen Brunson wins this round.
Okay, great.
Okay, my next fighter is going to be the gluon field.
Oh.
Remember, the gluon is the force-carrying particle for the strong nuclear force.
Okay. Okay, then again, I picked a couple of these based on just scrolling my feed and just names that were popping up frequently. So I'm going to go with Zohran Mamdani.
Yes. The gluon field considers bowing out as a sign of respect, but knows that Zohran would want a fair fight.
Yes, absolutely. Absolutely. But he is good against going up a strong force. I'm just saying.
What do you think are going to be his special moves in this fight?
Oh boy. Okay, remind me another thing about the gluon.
No, this is about your fighter.
She said
this is about your fighter.
Okay. Definitely the sneak attack.
No one sees him coming.
Yeah, exactly. No one saw him coming.
True. Okay, maybe is he gonna try and use the power of socialism, like the power of community?
Yeah, that's another wave.
Okay. I'm so glad you said so, because the gluon field, as the force-carrying particle responsible for the strong nuclear force, has the ability to bring things together.
Ooh, okay.
But also to take away that connective tissue.
Yes, that sounds about accurate as to current events.
So I think that the gluon field is going to counter Zohran's attack by dismantling the glue that holds the socialist communities together.
Right. That is a strong offense, but I think he's also good at charging other particles. So
rallying.
Yeah,
I see you trying to rally. I think that any type of communal strategy, any type of teamwork strategy is not going to work against the gluon field.
Okay.
And then I think the gluon, seeing it has the upper hand, is going to come in with the fact that it is the strongest force, and will probably just with the utmost respect, push Zohran out of the ring.
Dang.
Yeah. All right. For my third and final fighter, because we're now tied 1-1, I'm sending out the strange quark field.
Okay. Because I have two opponents in the wings ready. But I'm trying to decide which one would be best against the strange quark field. Because, yikes, I feel like they might both be out. So I'm going to go with Zendaya. If that tells you anything about my Twitter feed, as it should, because that's what it is. It's Zohran Mamdani, Jalen Brunson, and Zendaya and Tom Holland being cute all over the world.
Oh, I want to live in your news feed. Excellent. Okay, I'll go first this time with what I think some of the strange quark's strengths are. It's a fairly heavy particle. Not the heaviest, but it can throw some weight around, and it has something called the strangeness property. This was discovered in the 40s, I think. Before we even discovered quarks, we discovered that there are strange particles that seem to resist decaying into other particles. So the strangeness of the strange quark is its ability to resist being torn apart. essentially. In D&D terms, the strange quark has a constitution modifier out the wazoo.
I love that, because I mostly understand that now. Okay, I see your opponent, and while I think that, like, she might be outmatched by this particular strange quark field, I do think she's going to put up a good fight, because Zendaya has been a public figure since she was a child, and she has resisted any kind of rumors. She has not gotten into any kind of trouble. She has gone on to star in some of the biggest movies around. She is in like 3 huge movies this year. So she's got a lot of star power. She's got a lot of community behind her. She's got sharp skills and wit, and she is also charming, and she has the whimsy quark.
The charm quark is right there.
You're right. Yes. I was like, there's gotta be, but I forgot it. So we're gonna go with the charm quark.
Yes. She is coming with the charm offense.
Yes.
Wow. You know what? I think that they might actually reach a standstill.
Really? Great.
And need to tap in their seconds.
Oh,
so you said you had a fourth that you were thinking of bringing in.
Yeah.
You've been saying James Bond.
I have been saying James Bond, but actually I'm going to bench him, because who else is Zendaya's second but Spider-Man?
Oh, not Tom Holland, but
Tom
Spider-Man.
Holland, Spider-Man, yeah.
Perfect. Okay.
I'm going with Spider-Man.
Okay, perfect, because I'm bringing in the electron field.
Okay.
The electron is a very low mass particle that moves very quickly and is like Spider-Man, and is one of the particles that is more likely to quantum tunnel.
Oh, okay. I am like 95% certain that Spider-Man has quantum tunneled in one of the comics, because he is also he's in the Marvel Universe with Ant-Man.
Okay. So the electron's going to try and like quantum tunnel through. Seems like Spider-Man is also quantum.
Strong. Yeah, and he has a lot. He's probably done some quantum tunneling himself. He knows a lot of good scientists who could help him out. Bruce Banner, Dr. Pym, the guy who did the Ant-Man stuff in the Marvel Universe. So yeah, he's good. He's got Reed Richards, who is also very smart, and so he has like good people who know their equations.
Okay.
He's also a very smart science kid himself.
He got good grades in school.
Yeah.
When he showed up. That's what matters. You know what? I think that the electron, it puts up a good fight, but the strange quark is down. Zendaya is down. The electron's giving all it can, but I think Spider-Man just knows too much.
Yeah,
just has a little bit too much of an advantage, and so it's close. But I think Spider-Man wins.
I think so too. He would know about, like, he would either know or get the knowledge about this stuff to be able to like really untangle it.
I think the electron would try and pull some like, magnetic stuff, magnetic attacks, but that counters with the web. So I think it comes to a very narrow defeat by Spider-Man.
Yes!
Congratulations.
I won. I won the quantum episode game. That I would have never guessed.
The Quantum Mania belt is yours.
Thanks.
You're welcome. All right,
also
listeners.
An Ant-Man movie title.
Quantum. Yes, I know. That's why I did
wanted
this.
to make sure, bestie. I just wanted to make sure, bestie.
I know I grew up in a log cabin, but I don't still live under a rock in the woods. Okay.
Okay.
I'm cultured now.
You are, bestie. You are.
And listeners, no matter how cultured you are quantum and you are space.
Yeah. Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram, or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm at ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.